Okay, today we're going to see this introduction to some basic concepts to block diagrams and bond graph models. And to that effect, I have just a simple example that I would like to portray. But before that, let's just look at some very basic concepts of what we are talking about. So what we're going to do is let's go to my web page here. And let's look at this, as I called it, basic concepts in here, single and multi-pro devices. So I will disappear from now, and then we'll go on. What I want to first show you is this slide. You have this um, these four systems in there. One of them is in the mechanical domain, as you can see over here. The other one is in the electrical domain. The other one is in the rotational mechanical domain. And this other one is in the hydraulic domain. Domain means a set of variables within the realm of systems in one domain. Like in this case, we are doing mechanical, electrical, rotational, and hydraulic systems. Perhaps let's see over here. That would be a little easier here. You have this, when you have it in the mechanical domain, you measure the force in newtons, the velocity in meters per second. In the electrical domain, you measure it in volts and also in amps. The torque in newton meters and the angular velocity in radians per second. Pressure in newtons per meter square and the volume flow rate in meters cubic per second. What I'm trying to tell you is that the variables that you see on the left-hand side, they are one type of variables that we're going to call them efforts. And the ones on the right-hand side are a different kind. We're going to call them flows. So among the efforts in the left square is like a family of variables that are similar to each other. They're cousins of each other, but they are in the different energy domains. So what I'm trying to say is, if you have a mechanical system where the force is measured in newtons, the counterpart on an electrical system is the voltage, or the counterpart on a rotational system is the moment in newtons meters, and the pressure, of course, in newtons per meter cubic, per meter square. On the one on the right-hand side, the velocity, the current, the angular velocity, and the volume flow rate are same type of variables. Each one of those is acting in a different energy domain. Yeah. So in here you have the situation where the product of these variables times these variables is always power. So the product of newtons times meter per second is joules. Volts times amps is joules. Joules per second, yeah. And then meters, radian per second. This is also a unit of power. Newtons per meter squared times meter cubic per second is also a unit of power. Yeah. So In here, the variables that we use are we're gonna call it E for effort variables and F for flow variables. Some books call it through variables and across variables. Others talk about the cause and effect variables. They amount to the same thing. In here, one more clarification that we would like to make is that the flow variable is the derivative of the position. And position, we are going to generalize it by the letter Q. And the letter P is going to generalize the momentum. If you differentiate the position, you get the velocity, right? So F, which stands for velocity, is dq dt. And E, which stands for force, is the rate of change of momentum, which is dp dt. So the little picture that you see here shows the different kinds of relationships between the variables. Like in this case, the effort is dp dt. In this case, the flow is dp dt. But we use the power variables P and Q. Okay? So in here you have this little tetrahedron. It's known as the tetrahedron of a state, Painter's tetrahedron of a state, in honor of the inventor of this technology, who was a professor at MIT in the 50s. Now you see, this is a more clear representation of what we're talking about in the kinds of variables. Like all the efforts are listed here with the units. All the flows are listed here with the corresponding units. All of them in the displacement here with units. All the momentums are here. Now, you see, we are talking about 4 variables, and if we have 4 energy domains, that's 16 variables. What Painter is saying is, you know, guys, we shouldn't have to learn 16. Why don't we just learn 4? And every time we talk about an effort variable, and the system is mechanical system, we know we're talking about newtons. Every time we talk about an effort variable and it is an electrical system, we know that the effort is measured in volts. Same thing. If we talk about a flow in an electrical system, it's measured in thank you. It's measured in the velocity is measured in meters per second. The displacement in meters, the angle in radians, the charge, and so on. So what Peter is saying is, guys, we shouldn't have to be learning all these variables. Why don't we just learn these 4? And we're gonna need them: E, F, P, and Q. No, this Q and P. So if you have variables that are in the mechanical domain or in the rotational domain or in the electrical domain and on the hydraulic, we might as well forget about the 16 variables, but we would care about these 4 variables. Okay, if that's the case, why don't we look at a simple graph, simple model where we can actually look at the particular system. This is a system that you use when you started your car this morning. You started this morning with a battery giving a voltage to the starting motor, and the starting motor um, rotating this so-called Bendix in there, which is a little gear that starts your car. Okay? But over the years, and what the intent of this whole thing was, is to make it easier for people to understand how to model systems, not to make it more difficult. And the author of the textbook in your class, Professor Dean Karnoff, came up with this idea that we can use words instead of the technical elements, just to make it easier. So if I had my way to change the word bond graphs, I would change it to connection graphs, even easier. You have the battery, and then you have a motor, and then you have the gear, the Bendix. The battery interacts with the motor through the voltage and the current. The motor and the Bendix interact through the torque and the angular velocity. No? So we could create real models of things. We could create, using these words, generate a connection graph of the elements that make up a car. This is an entire vehicle modeled after this um, idea, where we have the engine, and you see the engine by itself. It is in fact a control system, because the throttle controls how fast the engine is rotating. We also have a situation where the um, the um, the engine connects to the clutch, even if on a manual, or even of an auto, even if the car is an automatic transmission car, it will connect this way. How is that happen? Because the motor gives the rotational velocities, this angular velocity controls controls how fast the engine is rotating, and the clutch controls how it connects to it, right? Okay. After you go through the clutch, you see you have this also communication, you may say, to the gearbox through a moment and an angular velocity. And the gearbox in itself is also another control system. It's amazing how many things are controlled in a car. Okay, when you switch in one gear, it does, goes maybe slower, but goes fast. It goes, has a lot of torque. Or you switch another gear, it goes faster, and so on. So you get to the drive shaft, and then the drive shaft connects to the differential gearbox, and that differential gearbox connects to the wheels. See, you haven't gone so deep into the subject, but I am pretty sure that everybody has gotten the idea now what I'm talking about. Could we create a language where we connect just parts of a system and that they will communicate with each other? The answer is yes. We can create a language with symbols that represent each one of these elements. And by the computer recognizing how they are connected, you will be able to come up with a computer model that represents reality. So what we're doing right now is some basic models of the basic theory behind bond graph model. But the bottom line is, can we create a connection graph where these things don't have to be the words, but they have to be elements that the computer recognizes and what the system does. So let's just take a look at a technical concept called the causality. Causality comes from cause and effect. So you have in here both of the methods that we are talking about in the most elementary way. This is a block diagram between element of a system A and element of the system B. If A sends a signal to B through this variable E, B responds with a flow. In other words, I have an object, and if the object I apply a force, the object moves. So the action was the force, the response was the velocity of the object. Do you see my point? Or vice versa, could be if we specify the velocity, then the force gets generated. My point is that if we go to the elementary, you may say, individual elements of a system, if A is one element and B is the other, this block diagram could also be represented by the symbol here, which represents the entire thing here. But because this is new, I need to show you how to read this. Do you see the green line in there? Do one thing for me. As if you hold the line and you're gonna push it to the right. So that would be something similar to this. Let me just let me see if we can write this. See here, let's say this is as if you had, see, there is your blue hand. Right there, there's your hand. And if you press it to the right, this is like a little piston that you are holding and pressing it there. You see, this is the effort right there. So the effort goes from A to B, but the flow, which is this, the green line, goes from B to A. The opposite is true here too. You see, let's say that you are in here again, there's your hand. There you go. And now you say, okay, if you press it to that B inflicts an effort on A, is represented by this crossbar. And the response of A is represented by the green bar. So if you read the bond graph like this, you're always going to read the effort variable here, and you're always going to read the flow variable over here. If I do it the other way, like here, if I do this, this is like, this is B, and here you have A, Yeah, and in here you have this. I don't know why we have this. You have the bone graft model like this. All right. So let's go on. You need to create all these things, only 9 elements, which is great. We don't have to learn lots of elements to represent just about anything under the sun. We are going to need 2 source elements, one source of the effort variables, one source of the flow variable. You're going to need 2 junctions, which we're going to use the symbol 0 and 1, and you're going to use these 5 elements. You have an inertia element, which are for elements that store the kinetic energy. You have the C elements or capacitive elements, which store the energy here for for springs or so. You have the R element, which is, so in other words, the springs store potential energy, right? The R element actually does the opposite. It actually creates resistance, dissipates energy. And then you have this transformer element, which is like the gearbox on the model that we just saw. It's a conservative element that actually transforms one angular velocity into another, or one torque into another torque, or one force into another force. And then you have the gyrator element, which is also a type of transformer. Is used, in fact, sometimes it's called a cross transformer because it's like in motors, in electrical motors. The voltage is always related to the angular velocity, and the so this is that's how a motor works, or the current is related to the torque. You see, so these are the only elements that we need. So I think at this point I would like to see if we go and do an example, and an example of how we go about modeling this. So let's give it a try.